Okay, so now we're doing example 5. And this one says it gives us a plane, x plus y plus z equals 1. That's a plane. And it gives us that plane cuts the cylinder, x squared plus y squared equals 1, and an ellipse. So if we had the cylinder, and this plane cuts through it, this cross section would be an ellipse. And so we need to find the points on the ellipse that are furthest and closest to the origin. So because we're dealing with the origin and we need distance, we have the equation f of x, y, z, x squared plus y squared plus z squared. So that's like a distance formula from the origin squared. And we have these two constraints. So this can be g of x, y, z. So this is the plane, which the equation is x plus y plus z minus 1 equals 0. We just move the 1 over inside equal to 0. And this cylinder, we can call h of x, x squared plus y squared minus 1. This is also set equal to 0. Okay, and so when solving with two constraints, we know from before the gradient of f equals a scalar lambda times the gradient of g, but also can be mu, just any other scalar, times the gradient of h. So it works like that. At this intersection point, the gradients would be the same, just multiplied by a scalar. So we can do the same, this being f, our gradient there is, so in respect to x, y, z, we find the derivative 2xi plus 2yj plus 2zk. Okay, set that equal to lambda times the gradient of this g of x, which was our plane. That's just mu times mu I plus mu j plus mu k, and then 1 is nothing, and then, oh, sorry, these are lambdas. It doesn't really matter which scalar we use, but we had it organized earlier. And then plus, so then for our cylinder, that's the one we use mu for, the scalar. So 2x mu I plus 2y mu j. Yeah, so this is our full Lagrange equation. And so if we factor this right side of the equation to to keep our I values, this like the I, j, k, keep it in I, j, k notation, we'll have mu plus lambda plus 2x mu I plus lambda plus 2y mu j, and then lambda k equals the same, 2xi plus yj plus 2zk. So from there, we need to solve these for our lambda and mu values. So we know 2x equals lambda plus 2 mu, and 2y equals lambda plus 2 mu, and then 2z equals just lambda. Okay, so since we have lambda solved for as 2z, we can plug it into here or here. So we get 2x equals 2z plus 2 mu, and then if we plug it into this lambda, 2y equals 2z plus 2 mu. So from this, we can find that, or we can factor this out and divide by 2. So x equals, make these z's, x equals, how are we doing this? 2 times z plus mu, and y equals 2 times z plus mu. Right, so in this position, we know that x and y equal each other. X equals y. Or if they don't equal each other, that means z would have to equal 0. So these are our two possibilities. If z equals 0, then x and y equals 0. Otherwise, if z doesn't equal 0, then x and y just have to be the same thing. So we can plug these back into our original equations up here. And since we know, so g of x, y, z equals x plus y plus z is now 0. Minus 1 equals 0. So from this, and okay, we also know h of x, y, z equals x squared plus y squared 1. So from this, we can, if you solve this, you can get either x equals 0 and y equals 1 and z equals 0, or x equals 1, y equals 0, and z equals 0. We knew z equals 0, that's what we plugged in. So we found out in both situations either x or y equals 0. So that gives us the point 1, 0, 0 or 0, 1, 0. These are important points. These are the critical points we found, but there's also the possibility that x equals y. That was another way to solve this equation. So if we plug that back into our original equations, we'll just do it up here. So x equals y. We know that x plus, so for a g of x equation, or g of x, y, z, forgot to write that, x plus z minus 1 equals 0. So, we have what, z equals 1 minus 2x, if you add the 2 x's over and move to the other side. So then, okay, so we need that equation, sorry. We know h of x, y, z, if we use this bottom one, we have x equals y, so x squared plus this y squared becomes x squared minus 1 equals 0. So 2x squared equals 1, and x equals this divided by 2 square root of 1/2. So because we know x is the plus minus square root of 1/2. We know x, you can plug it back into here. It's equals 1 plus 2 times square root of 1/2. Wait, pause it.